Hey guys, I hope you're all doing good. In this video, I'm going to be talking about the equations that govern the flow inside the boundary layer. So if you take up any standard book on boundary layer theory, then you will see that inside the boundary layer, the following equations are valid. So these are nothing but your Navier-Stokes equations. So this is your continuity equation, this is your momentum equation, and this is your energy equation. Now all of these equations are valid inside the boundary layer, and you can see that some of the terms are missing. That is because inside the boundary layer you can neglect some terms based upon order of magnitude analysis. So in this case, what we have is we have this final set of equations with which you can simulate boundary layer in any type of a geometry. But as we have been seeing so far, we have always used a turbulence model, right? So whenever we set up the shock flow problem or the conjugate heat transfer problem, we always used a turbulence model. Why is that? Well, if you look at these three equations, if you solve them, they are completely capable of giving you solutions for both laminar and turbulent flows. And if you do that, then people would say that you're performing a direct numerical simulation. So DNS is a technique where people take the Navier-Stokes equations and solve it, and they're able to capture everything, including turbulence, and they're able to capture everything. So then why do we need a turbulence model? Well, here is a simple example. So in this image, on the left hand side, we have free stream coming up and we have a stationary plate. So flow is actually flowing over a stationary plate, and initially the boundary layer is going to be laminar, and after some time it's going to become turbulent. And then if I take the turbulent region and if I put a velocity probe, right? So let us say that this is the location where I'm probing the velocity. Say that I'm able to measure the velocity in that region as a function of time. Then I'm going to basically get a profile like this. So if I look at the velocity at the probe location, it's going to be continuously fluctuating. So this small, and if I kind of measure the frequency of this fluctuation and inverse that, then I can calculate something called as a turbulent time scale, right? So this is the time scale associated with that fluctuation, and this time scale is really small, and this occurs over a very small distance. So this is where we have a challenge. So if I take my original governing equations and if I am able to solve it so that I integrate only over small time steps and I have a huge number of computational cells, then I don't need a turbulence model. Okay, but this approach is quite impractical for engineering simulations that people attempt these days, right? And that is why we are using a turbulence model, so that we can still capture the effect of turbulence by using a coarser grid and a larger time step. So what is the logic that we are going to apply here? Well, we are going to take these governing equations and we are going to be integrating it over a time that is much larger than the turbulent time scale. So this is called as the averaging process. And then we apply something called as a Reynolds decomposition, and we convert this original set of equations into a form that is called as the Reynolds average Navier-Stokes equation. We then use these equations along with the turbulence model to simulate turbulent flows. Now in this process you will end up with some unknown terms that have to be modeled, and these are some of the things that we will be learning today. So the first step that we need to take is to split your velocity components or any other flow variable into a mean component and a fluctuating component. This is what is called as the Reynolds decomposition. So for example, if you look at this u equation, you can see that this u is your instantaneous velocity at any point in time and space, right? So that is why u is a function of x, y, z and time. Now what we are doing is we are taking this velocity and we are splitting it into two components. You can see that one component is just a function of space and the other component is a function of time and space. This right here is the averaged quantity, right? And to be specific, it's a time averaged quantity plus a fluctuation. All right. Well, how far are we averaging? Well, we are averaging it for a time that is much larger than the turbulent time scale. Why are we doing this? Well, if you take a look at all of your engineering quantities, this is the time that people are interested in. This is the quantity that people are interested in. The averaged quantities are great, but say that you're simulating flow over an airfoil, you need the time averaged drag coefficient, correct? Which is what is interesting to you. If you have the instantaneous velocity components, you would still have to time average it, right? And that is what is the motivation for Reynolds decomposition. Now, if we look at the expressions for u bar and v bar, these are nothing but time average. So we take 1 by t int. So t int stands for the integration time, and we integrate it from 0 to t int, and we integrate the instantaneous velocity. And that is why the u bar that you get is just a function of x and y, because since you're integrating it, you're kind of computing an average quantity, right? And this average quantity doesn't change with time, and that is why u bar is only a function of x and y. All right, now another interesting property that can be derived for this time integration is when you integrate your fluctuating component, it's always going to be 0. So what I mean by that is, if you do 1 by t int, and if you integrate this, and if your integrand is your fluctuating component, this is going to be equal to 0. And this actually leads to a lot of simplification. And let's kind of derive why this is the case. So if I take my original decomposition, u of x comma y comma z comma t is equal to u of x comma y, and this is u bar, plus u prime of x, y, z, and t, right? So this is Reynolds decomposition, and say that I'm time averaging this. So let me first do u of x, y, z, t integrated from 0 to t integration time, 1 by t integration is equal to t integration, 1 by t integration 0 to t int u bar of x comma y plus 1 by t integration integral 0 to t integration u prime x, y, z comma t. All right, so now what is this quantity? Well, this quantity is nothing but u bar of x comma y comma z, correct? This is basically your time averaging, right? And that is your bar quantities. What about this guy? Well, what happens if you time average an average quantity? Well, you're just going to get the average quantity. And let me kind of prove this to you. So for example, let us say that your starting point in velocity is 0, and your ending point in your velocity is 1 meter per second, and this is after 1 second, correct? Now if you average this, you can say that your u average is going to be 0.5 meter per second, correct? Now what happens if I average this quantity again? Well, you can think of it like this. Say that you have a velocity component u, instantaneous velocity, which is always a constant, and this constant is equal to 0.5 meter per second, and this goes from 0 to 1. What if I compute the time averaging on this again? Well, that's also going to be 0.5. In other words, this quantity is also going to be u bar x comma y comma z, plus you have your 1 by t int 0 to t int u prime of x comma y comma z comma t. This and this are going to get cancelled, and we can say that whenever we are integrating, especially doing a time integration on our fluctuating components, that integration is always going to result in 0. So the idea is, when you integrate for a longer time, these fluctuations are basically tend to 0. That's the idea there. And this can be applied, or this rule can be applied not only for your velocity components u prime, v prime, and w prime, but also for other components like t prime, where t is the temperature. And this can be used to derive a lot of rules, right? So whenever you are taking, and this result can be used for a lot of simplification. Whenever there's an integral quantity where you're multiplying a time averaged quantity with the integral of a fluctuating component, that result is going to be 0, right? So this result that we have obtained is very useful in simplifying our Reynolds average Navier-Stokes equations. So now let's apply this integral rule to the continuity equation. So you have dou u by dou x plus dou v by dou y equal to 0. The first step is to apply the decomposition. The second thing is to integrate this entire equation with respect to time and do a time averaging. Okay, so let's just so on further simplification, and then if I split this equation into multiple integrals. Okay, so it's quite easy to see that this right here, anytime we take a time integral of the fluctuating component, that is going to be 0, right? So these tend to cancel each other. And your u bar is not a function of time. So I can actually take these derivatives outside. And now if I apply the limits for the integration, okay, so the end result is that we get our continuity equation in terms of the time average quantities, because this right here is going to cancel each other. Okay, so that's pretty interesting result. In other words, your time average velocity component satisfy the continuity equation. All right, so now let us simplify our momentum equation. Okay, so the first thing that I'm going to do is I'm going to take this density and I'm going to move it to the right hand side. And then what I'm going to do is I'm going to take this mu by rho and I'm going to replace that with the kinematic viscosity. Now on the left hand side, I'm going to basically add a term which is nothing but the x component of velocity multiplied by the continuity equation. The reason why we are doing this is to convert this equation into a much more suitable form. As you can see, this is perfectly valid because dou u by dou x plus dou v by dou y is equal to 0. So we are just adding 0 to the left hand side, which is perfectly fine. So then what I can do is I can take this term right here and I can combine it with this particular term. Now to further simplify this equation, we are going to be using the product rule. So if I take dou by dou y of uv, that is nothing but u times dou v by dou y plus v times dou u by dou y. And as you can see, this term right here is exactly the same as these terms. Now as you can see, the terms in these two boxes are exactly the same, which means I can simplify my equation to we are going to apply one last simplification to this particular term, and we will be ending up with the following equation. As you can see, dou by dou x of u square is nothing but 2 times u times dou u by dou x. So now we are ready to apply the time integration and also the Reynolds decomposition. Now if we expand this a little bit more, we'll end up with the following terms. Now as we have already seen, time averaging a fluctuating quantity is going to result in 0. So this term is going to be 0. This term is also 0 because when you integrate it, u bar is going to come out of the integral, and that is going to get multiplied with the integral of u prime, and that is going to result in 0. This term is going to be 0. This term is going to be 0. Alright, so if we clean up this equation a little bit, we are going to get All right, so now this actually brings us to a very interesting result. If you actually look at these terms were actually present in your original momentum equation, except that the variables are not time averaged. So here you are having all these terms. For example, here every term is time averaged, right? In the original equation, it's the instantaneous velocity. So during the time averaging process, you are introducing two additional time derivative terms. Now this right here, these two terms don't necessarily cancel out to zero. So for example, when you are integrating the instantaneous fluctuations as a function of time, we proved that that is going to be zero, right? So the idea is, if you're looking at a long enough time, the fluctuations have both positive and negative values, and they are equal in number, and that is why when you average them, it is becoming zero, right? So you can think of that as, a curve like this. So for example, here this is our first scenario. So if you take u prime, say that it's fluctuating between 1 and -1, right? So if I average this, I'm going to basically get a zero average, correct? But if you take u prime square, that does not time average to zero. Why? Because you take -1 in u prime, when you square it, that becomes a positive value. So when you're integrating a positive number, it's basically like you're adding a series of positive numbers, and that is never going to be zero, right? And that is why this term right here, it's actually not equal to zero. What about this term right here? Well, that is also going to be interesting. So if you take u prime and v prime, right, now you cannot be sure that, so u prime basically says how the velocity is fluctuating along the x-axis, and v prime is saying that how the velocity is fluctuating along the y-axis. Now turns out there is a correlation. That is, for example, say that you have a flow field like this, right? So flow is taking place like this, and you're looking at near the wall. So let us say that I have a positive fluctuation along the y-axis. So this is my y-axis, right? So if I have a positive fluctuation along the y-axis, and since it's a boundary layer, right, near the wall the velocities are lower, and away from the wall you're recovering your free stream velocity, correct? So when you're having a positive fluctuation along the y-axis, you take the fluid with a low momentum, right, meaning low velocity, and you're injecting that into a zone of high momentum, right? And what is this going to do? Well, this is basically going to slow down your x component of velocity, right? It is very similar to this. So consider that you have a road like this, right? And this is actually a multi-lane road, and you have cars traveling roughly at the same speed, right? So right, I have several cars here, right? So let us just pay attention to these three cars. So what's going to happen is these three cars are going to go like this, right? And say that there's a small road here through which there's a car that's trying to come like this. So this is your v prime, fluctuation along y component. When this happens, these two cars are not disturbed. They can continuously, drive past, assuming that this car right here doesn't come that fast. But this car right here has to slow down, correct? Has to slow down because of this new injection of car. Similarly, when momentum is flowing in the y direction, especially when it's a low momentum fluid, that's going to cause a slowdown. And this is what you call as a correlation. That is, your u prime, that is fluctuation along the x-axis, is somehow related to the fluctuation along the y-axis. In this case, a positive increase in v prime is going to cause a negative in u prime, right? And hence, if you take the product of u prime and v prime, well, that is most likely going to be negative, right? Because if you have a positive number and when you multiply that with a negative number, the result is going to be the same. The result is going to be a negative number, right? And when you take the time average of a quantity that is completely negative, the result is also going to be a negative number, right? In other words, this term is also non-zero. However, what we are going to do is we are going to make an assumption. So since this is a boundary layer, right? So for example, if you take a boundary layer, this right here is going to be my x-axis and this is going to be my y-axis, right? So the idea is the boundary layers in general are pretty thin, right? They're pretty thin, like they're really small, correct? They're really small, especially when you compare it to the size of the plate. So the argument that we can make is that the gradients in your velocity components, correct? The gradients in your velocity components are going to be much more stronger in the y direction when compared to the x direction, right? Because in that small space, in that small boundary layer, your values for your velocity components changes a lot. But along the x-axis, the changes do not take place a lot. And hence, what we are going to do is we are just going to neglect this term. And this is a very important assumption and is true only inside the boundary layer. Now you can do something called as the order of magnitude analysis to kind of estimate this assumption, to estimate the validity of this assumption. So for now, we are just going to say that this term, this entire term is going to be equal to 0. One last simplification can be done to the right hand side terms. So in the right hand side term, one thing that I can do is I can actually take 1 by rho times dou by dou y outside, and that is basically going to give me, mu times dou u bar by dou y plus rho by t integral, and the derivatives and the integration can be interchanged. That's not a problem. So I can do time integration u bar v bar and dt, right? So why did we do this simplification? Well, this actually brings us to an excellent point. So you can see that first of all, this right here, this entire thing right here on the left hand side, these are my inertial terms, right? But these are my inertial terms that have been calculated based upon the average quantities. So this right here is my pressure gradient term, and sometimes what people do is they take delta P divided by rho, and that becomes something called as the kinematic pressure gradient. All right, so this right here for now is just my pressure term, and all that is left is the diffusion terms, and especially diffusion of momentum. And we are basically saying that your momentum can be diffused in two ways. One is through your molecular viscosity, right? And the other term, basically this time integral term, that represents diffusion of momentum because of turbulent motion, right? And this thing right here is momentum diffusivity because of turbulence, right? So you can kind of say that there are two components that are affecting how momentum is taken, which basically dictates how momentum is diffused from your boundary layer to the outside of the boundary layer. Okay, so basically this is your Reynolds average Navier-Stokes equation. Now the only thing that we do not know is that time integral right there, and turbulence modeling is all about capturing that particular term. In fact, this right here, this dou by dou y multiplied by mu dou u by dou y, so that is your shear stress based upon molecular viscosity, and if you take the derivative of this time averaging term, then that is going to be your Reynolds stresses. So this basically here is also called as your viscous stress, and this right here is nothing but your Reynolds stress. And getting this Reynolds stress correctly is what turbulence modeling is all about. Alright, so I hope you learned about the RANS approach in this video. In the next video, we'll be talking about the law of the wall. Thank you. Bye.